Everybody, I just want to take a few minutes to go over the level 3s with you to make sure you understand how to do the drawings that we did today on Pear Deck. Right here, we'll start out. Obviously, we see that there's a trench and a volcano, so we know we have a subduction zone here. And those are caused by convergent boundaries. We can see that we've got one plate that's out of the water and one plate that's under the water, so that gives us our continental plate and our oceanic plate. And because we know these arrows are going towards each other, we also know that the mantle convection current must be moving in the same direction as the plate. So right there, and you can see this person did a nice job, matched up their blue, matched up their red, matched up the pink with the convection currents, and then black over there. So they can also look at this and see, yes, I did all 4 of those criteria. Okay, so here's one that they've got a convection current, the plate movement going towards, but if you follow these arrows, they are actually going away from each other. So make sure that you're drawing your arrows clear enough that you can understand. They have everything correct except their convection currents would be carrying these plates away from each other. All right, let's move on to the next one. Let's see. Here we've got a nice divergent plate, and again, they did a nice job. They've got red matched up for the divergent boundary. They're going away. This is going to be a mid-ocean ridge right here. So we have oceanic plate and another oceanic plate. We have our convection currents going away from each other, so the plates are then going away from each other. That's correctly done. Again, this one here looks nice. The arrows are matched up between the convection current and the plate motion. So this one here is a little bit different. It is actually a ridge that sticks out of the ground. So it is a mid-ocean ridge. It's going to be a divergent boundary. This person has everything except they don't have the directions for the plates or the direction for the convection current, so it was not completed. So this one here is completed. We have 2 oceanic plates. We have arrows for the plate motion going away from each other, and the convection currents also moving in that same direction away from each other. So this one here, they have it as a convergent boundary, which it would not, because convergent boundaries, there's no trench here. Okay, if there was a trench, then it would work, but this is not. The split is right here where you can see the magma coming up. It's not going to work unless I actually had somebody do this today. Let's go over here. Unless it looks like this, and they actually drew in a trench and labeled the trench. Now this would work for a convergent boundary, but that's the only way. You would have to draw in the trench, so that's extra complicated for you. So I would think that you would want to just stick with the divergent boundary, making that mid-ocean ridge. Here we've got our mountains. So this would be Mount Everest. We have convergent boundary. We have plate movement towards each other, and we have the convection currents moving in that same direction. So this one is correct, and it's continental plate and continental plate. Same thing here. The arrows match. That's good. They're both moving towards each other. And we have continental at a convergent boundary. Then that takes us to our last one here. Transform boundary. We do need to run back, check on the types of rocks that would be present at each of these. This one here, this is moving that direction. This one's moving this direction. The plates match it with their motion. That's correctly done, continental, continental. This one could be oceanic to oceanic as long as they match because they are the same thickness. And you can see the only type of rock that would be created here would be metamorphic because of all this pressure at the fault line. So there would be metamorphic here. right? At this one, they're crushing together. We'd have metamorphic because of the collision. Down here, deep down in the mountain, there might be some intrusive igneous being created because of the lifting of the plates, but really it's metamorphic on that one because of the pressure in the collision. This one would be igneous, both intrusive igneous in here when this cools down, so inside the magma cavern or magma chamber would be intrusive igneous, and then when it explodes and erupts, it would be extrusive igneous when that splits. Same thing here. Intrusive igneous would be cooled in the magma cavern, and anything that came out when the fault split would be extrusive igneous. And then this last one, you're going to mostly get extrusive igneous building up this volcano. You might also get some metamorphic along the sides of the volcano where the magma comes up and heats. But I would say just stick with extrusive igneous and intrusive igneous on this one as well. All right, hopefully you guys have a good time studying, and this is helping make things a little more clear. Thanks for watching.